Hello, everyone. Welcome to our DinAmicI seminar. It is my pleasure today to introduce Adam Kanigowski from the University of Maryland, who will tell us about ergodic theorems along sparse subsets of the integers. Thank you.
All right. Thanks, Davide, and I'd like to thank the organizers for the invitation. Yeah, so let me start by some basic things. So the setup for this talk we'll have a topological dynamical system, which means we have a compact metric space and a continuous invertible map. Yeah, and then usually one studies invariant measures if one is interested in long-term evolution of the system. So, and the measures that one usually focus on are on singular invariant measures. So mu is an invariant measure if it doesn't change the measure of the set when we apply dynamics. And then the set of invariant measure is denoted by mxt. And a nice theorem of Krylov and Bogolyubov is that this set is always non-empty. So there exists at least one element there. And the definition of unique ergodicity is that a topological system is uniquely ergodic if this set is as small as it can be, meaning there's one measure which is invariant. And if you think about the way you prove Krylov-Bogolyubov theorem, so the fact that it's non-empty, the way the proof goes, it will tell you that essentially that we have a very nice characterization of unique ergodicity, which says that a map is uniquely ergodic if and only if for every point the ergodic averages converge to a constant, and the constant is given by the mean of the function with respect to that invariant measure. But this is nice. So shortly speaking, unique ergodicity gives us information about every point in the system. And this is a big difference with Birkhoff ergodic theorem, which tells us that any ergodic measure, for any ergodic measure, we have this convergence for almost every point. But the space of ergodic measures might be very large in general. So the behavior of these exceptional points from the point of view of one measure might be very wild and exotic. Yeah, and for this talk, I will be interested in we'll be interested in the behavior of every x in the system, but for more general averages than regular averages. So the general formulation of what we want to discuss maybe is given by the following thing. So we take an to be a bounded sequence, and then we hit it against our dynamical system. As you see, we study these averages. One could call them weighted averages. Yeah, and we normalize properly so that the trivial bound for this should be the supremum of f, or like the L infinity norm of f. But we want to know if we can say something more, if actually what is the limiting behavior of it. And in this generality, we can't say much, of course, because you can take various sequences. But maybe one first observation, and the sequence a n equals to 1 constant corresponds or is just the regular ergodic averages, which we then understand, for example, if we are uniquely ergodic, right? But as I said, from now on, we'll be interested in some other sequences coming from that are interesting in number theory. As I said, for general sequences, we can't say anything here. But you can take, for example, an to be the characteristic function of prime numbers or almost k primes, right? So here you would see, for example, if we are in case 2, you would see ftpx instead of ftnx. So you sample the orbital along primes. Or case number 4, you take a polynomial, so like n squared or k squared, and then your average would look like ftn squared. So you only sample along squares. And then a slightly different type of averaging happens if you take functions from number theory, such as the Mobius function or the Liouville function, which I'll define in a moment. But generally, so what I will discuss is these cases 2, 3, 4, and 5. And we'll be interested in the behavior for every point. I mean, I'll mention what are the results for almost every and for L2, for example, but the methods are very different, and the results are also, well, kind of in a different framework, I think. Yeah. So yeah, I'll just mention, as I said on this slide, the modes of convergence. So you can ask about, as I said here, you can ask about almost every point. You can ask about L2 convergence. So like almost every point would be the analog of Birkhoff ergodic theorem. You can ask about L2, which would be an analog of the von Neumann ergodic theorem. So L2 convergence. And you can ask about convergence for every point, which is an analog of the unique ergodicity, or the classical averaging. And it turns out that L2 convergence is easy to understand. And this is true for essentially, well, any sequence AN. So basically, what you use is spectral theory of unitary operators, and it tells you that L2 convergence follows from convergence of the corresponding exponential sums. So basically, for example, yeah, if you take primes and you want to understand L2 convergence of a dynamical systems along primes, it's an if and only if statement to understanding these sums. And this works for any sequence, just because in L2, the function f is there is a character that corresponds to it. So from that point of view, it's maybe not as interesting, just because the whole theory reduces to studying irrational or rotations and exponential sums. A deep result, I think, initiated by Bourgain is that for these sequences that I mentioned, convergence holds for almost every point. And this is a very deep result that uses a lot of stuff, and it's still active for maybe more general averaging. But for example, primes and polynomials and Mobius and Liouville, they all follow from what Bourgain did. And it requires, well, circle method and oscillation inequalities, lots of harmonic analysis. But we are not going to discuss that. It's, as I said, still an active, very active area, but maybe different from what we want to discuss. Yeah, so we'll be from now on interested in convergence for every x. And what I'll do is I will not, I think maybe at the end of the talk, I will state some results, but I'll more focus on discussing the history of methods that one uses for these various problems, and outline or highlight why they are difficult or why some of them had some progress recently and so on. Yeah, so if I go back a little bit, I think cases 2 and 3 are similar. I'll discuss them separately. 4 is another case in terms of methods, and 5 is yet another case. So I'll just go over them one by one. Yeah, so hopefully for now the setting is clear. We take it, so I'll repeat because then I'll just move to methods and some results. We take a dynamical system Tx, and you take your favorite sequence. Well, favorite by favorite, I mean, I will focus on the one on the list. You could be more general, but say primes, and you sample the fixed initial condition along primes, and you want to see what happens with the limit. Or you sample it along polynomials, right, n squared, and you see what happens with the limit. And the third case is actually the one I want to start with, because recently there has been, this case has seen a lot of development in methods, and I want to say, even though I'm not going to focus so much on this one, it's, I think, interesting. Yeah, So the third case was the Mobius function, which is defined, or the Liouville function. They are both very similar in terms of treatment and methods. So here are the definitions. You can think just about the Mobius function. So you take a number n and you take -1 to the number of prime factors of n, counted with multiplicities. And it turns out that the only, essentially, dynamically speaking, in terms of methods, the only somehow important part is that these functions are multiplicative. So the difference is that the characteristic function of primes is not multiplicative, right? I mean, obviously, if I take two primes and I multiply them, it's not a prime anymore. But here it is. So, and that's a very big difference. And there is a conjecture that was made by Sarnak, 14 years ago, that is very general. And I think it was a spark that motivated the development in this setting, which says that, if only I assume that my system has topological entropy 0, then these averages should have some decay, some non-trivial decay, small O of n. And the same for Liouville. So I'm focusing on Mobius, but really you can put essentially any multiplicative function here. So zero entropy, conjecturally, this conjecture is still open, plays the role of unique ergodicity for classical ergodic averages. So it's interesting that you might not be uniquely ergodic and still have a statement with Mobius, right? So horocycle flows, for example, are an example, which, yeah. And as I said, I'll focus on the methods and the difficulties. So here we've seen really a lot of results and development. And the reason, so I remind you what we are interested in. We are interested in showing that this is small O of n. Yeah, and as I say, there have been many cases, and I don't want to list them, but because there is a number of them. But the reason for say a success, even though the conjecture is still open, but the reason for quite a big success here was that two results. So one is a breakthrough result in analytic number theory of Matomaki and Radziwiłł from 2015, which says that the Mobius function exhibits cancellations, speaking maybe a little bit more in number theory language, on the typical short interval. So what you do is you take an interval from 0 to x is a large number, you chop it into pieces of size h, and the Mobius function is either 1 or -1 or 0, say. And what they proved is that for most of these intervals, you have cancellations from the trivial bound. So in most of the intervals of the form x plus h, -1 and 1, they occur with similar frequency. The main term cancels out, so you are left with small O of h. And the strength of this result was really that the window, the size of h, could be like log x. It can be arbitrary short with respect to x. The only thing we require, it goes to infinity. And multiplicative functions, among those that I mentioned, are the only ones for which we have such strong results. Generally, in number theory, we have results where h would be, say, a power of x, like x to power whatever, 1/2, 1/3, depending on the context. But never we had results about just h going to infinity. And then there was another work that maybe I won't mention, which generalized this for looking at expressions of the form μn e to the n alpha. So here, in this one, you just look at μn, but you can skew it by a character, and this is what they did. The Matomaki, Radziwiłł, Tao, Teravainen, and Ziegler. So this was one of the breakthroughs from number theory, but it also fed and had important consequences for many dynamical for the Sarnak's conjecture, for showing this for many dynamical systems. And the other one, which I think is more interesting for us dynamically, was what they call I think, Debussy, Katai, Bourgain, Sarnak, Ziegler criterion. And this is a general criterion on having cancellations in sums involving a multiplicative function, as you see. So what they said is that if I take a bounded sequence xn, any bounded sequence, and if for sufficiently large but fixed primes p and q, I have this type 2 sums being, I have cancellations there, then I will have cancellations in the Mobius, in the weighted average where I hit it against Mobius. Right? And if you translate it to dynamical systems, I mean, to Sarnak's conjecture, so your sequence xn is just ft and x, this then becomes studying something that Fürstenberg introduced, and it's called joinings. So you have these bilinear averages, where now what you're studying is the regular ergodic average, but your transformation is more complicated. So the transformation is now Tp times Tq. And this is a good news for dynamicists because joinings is a part of ergodic theory. So you can employ methods from the theory of joinings to study the Sarnak's question. And this is the second reason why questions around Mobius orthogonality and Sarnak's conjecture were successful. And I want to point out, you'll see it's going to be crucial later. In this context, the P and Q are fixed first, and then you let n go to infinity. So it's all about the quantifiers. And, you know, ergodic theory is very powerful tool whenever you have a fixed transformation and you don't care about rates. It's a very weak tool, or actually, well, I don't want to say useless, but pure ergodic theory doesn't give you any, right? So if I said that P and Q are somehow depending on n, you can't use joinings anymore, right? So, and this, I think you'll see later, this is also the many results, and we are quite successful. Okay, so that's for Mobius. So the two things to take away is that we were successful with studying multiplicative function, in particular Mobius, because there has been a breakthrough in analytic number theory, which allowed to treat short intervals, and because we have joinings. I mean, one can reduce this problem to ergodic theory. And now I want to discuss primes separately and polynomials separately, and we'll see what difficulties come up there. Yeah. So now we shift to primes, and I just give you one example. The simplest one is the prime number theorem, right? So we take a, say, uniquely ergodic dynamical system just to make it simpler. This assumption is not needed, but yeah, convenient. And then we would say that xt satisfies a prime number theorem if for every point this limit, so now we sample along primes, and pi of n is the number of primes up to n, right? So we need to normalize it properly. And you can do the same thing, I didn't write it, if you take, say, numbers that are products of 2 primes, for example, right? P and Q, or 3 primes, or more generally K primes. You can write the corresponding average. I'm pretty sure you know how it would look like. So I'll just focus on primes. And crucially, this is a different set of questions than Mobius orthogonality, because K primes, or even, I mean, primes in particular, are not multiplicative. I mean, the characteristic function of primes is not multiplicative. And we'll do it under the assumption that the entropy is 0. So you can imagine in a Bernoulli shift, for example, I can easily destroy this by taking a number. I mean, it's right. I could take a sequence of 0 and 1s where I destroy convergence at prime numbers. I mean, that's not difficult. So it's natural to at least assume something about the entropy. Yeah. And there are some classical results that I will maybe mention. Yeah, so if X is just a point, then it's a standard prime number theorem that this holds. If X is finite and T is a rotation on this finite set, then again, it's classical. If X is an irrational rotation, then it's also known by Vinogradov. So these are, as you see, some very old, relatively old results. I want to mention one result that we had is that it's not like Sarnak. So you can have a nice dynamical system that does not satisfy a prime number theorem. So by nice, I mean it's minimal, uniquely ergodic. You can put more ergodic adjectives there, but it's still not going to satisfy it. So it's not as simple. Actually, we don't know if there are any sufficient conditions for ergodic conditions that you could formulate that would imply a PNT. Yeah, okay. Just wanted to mention that this is different than Sarnak. Yeah, and then I don't want maybe to spend too much time on this. There are more results that I've listed here that are more recent on the PNT. So there are sequences, like two more sequences, Rudin-Shapiro sequences, if you know what they are, which satisfy a prime number theorem. And then you can cook up systems, so-called rank one systems that satisfy a prime number theorem as well. Then you can generalize this result. Sorry, let me go back. So if you look at number 3, you see that the prime number theorem holds for rotations. Irrational, I should say alpha is irrational here. If alpha is rational, then it reduces to 2. But you can generalize it to nil groups and nil translations, and this was done by Green and Tao. Sarnak and Dubis had a very interesting result saying that if you look at a horocycle flow and you look at the prime orbit, so orbit along primes, then it goes into every set of diameter larger than 9/10, I think. So they cannot prove density, they cannot prove equidistribution, they cannot prove a prime number theorem, but they know that the prime orbits are not concentrated, say they cannot live in a small ball. Yeah, and these are essentially all the systems. I mean, there are some more, but it's much different than Sarnak. It's much different than Mobius. And the reason is that there are essentially not, the methods are much more restrictive. And I want to outline maybe now the method, which I think is, by the way, by far the only one. So, okay, so here is if you still remember the Bourgain, Sarnak, Ziegler, the Bussy-Katai criterion, there was something that I called type 2 sums. And here it's much more complicated. So maybe you can first look at the conclusion. So the conclusion is that our sequence xn, which you can think of f, t, and x, equidistributes along primes, right? So we have a prime number theorem. And to get it, you need two types of conditions or two types of behavior be able to verify for xn. And the first one is usually called type 1 sums. So if you forget so all the normalizings and sums are done just to, have some, I mean, it's the right normalization. What is important is here the x dn. So here we are looking at arithmetic progressions, right? So we are considering x along arithmetic progression of size d. And type 2 sums is like the other criterion. So we have d1, d2. Okay, there are two main differences which really make our life, I mean, they are really substantial. The first one is that, as you see on the right-hand side, you need some rates. So the first one is 1 over log cubed. The second one is 22. Maybe you can reduce it a little bit. I think that's what they stated in the book, Duke, Friedlander, and Ivanets. But definitely you need some rates. And second thing, in this maybe complicated looking expression, is that the D1 and D2 and the D, everything, the step, say, for the step for type 1 sum and the steps for type 2 sums, they depend on n, right? So it's not that I fix D1, D2 and let n go to infinity. In fact, it's much, much, much worse. So the D1 and D2 should be as big as n to 1/3, for example. I mean, almost, typically, to get the PNT. So when you look at these expressions, the thing maybe that you should take away at this point is that no chance, at least it seems, no chance I can attack these problems by any tools in ergodic theory, right? And there are two main obstacles. There is the log terms here. So I need rates. And second, I don't even have a transformation. So maybe I have it on the next slide. Yeah. So that's the big problem, right? So which is written here. So we need something of that. We need to control sums, type 2 sums, let alone, I mean, type 1 as well, but type 2 sums for d1, d2 being a power of n, small power of n, which, I mean, doesn't, ergodic theory is not going to do it for us. And typically the C1 is a large number. So C1 is 1/3. It's not, it's not only, yeah. So one thing that I want to mention is that we were able recently with Giovanni and with Max to weaken this criterion if you want what's called semi-primes or 2 primes. So if instead of prime numbers, you're interested in 2 primes or products of 2 primes, then you need only type 2 sums of level n to epsilon. For any, so, epsilon can be arbitrarily small. So it's still not ergodic theory because the d1 and d2 depend on the epsilon, on the n. But, yeah, but at least you've created 1/3. So C1 was typically 1/3 primes to any arbitrary small power in case of semi-primes. So there is some gain. And in fact, we used it to show 2 primes theory, so that horocycle flows equidistributes at products of 2 primes. But I don't want to go there. Yeah. So that's maybe the story with the primes and 2 semi-primes. I think this criterion that we proved recently has some potential to be used in for some other systems. For primes, I mean, it's difficult just because you need the 1/3. Yeah. Yeah. So, I mean, that's about primes. And now maybe the last part that I want to discuss are polynomials, which again require different, I mean, the methods are slightly different. Yeah. Okay, so results for polynomials, I would like to mention. And I mean, and what is the theory? So yeah, if you look at the simple cases, so P of n is a polynomial, like n squared, for example. Then for rotations, this converges for every x. And this follows from just exponential sum estimates, which follows from van der Korput. I'll mention van der Korput in a second. And you can generalize it to Neal systems again. So that's what happens. But the method for polynomials, at least in these 2 cases, is different because you have what's called the van der Korput inequality. So polynomials behave like n squared behaves in many aspects different than primes, right? The reason being that primes are, like if you take n squared and n plus 1 squared, right? These 2, they differ by a linear phase, right? So the van der Korput is based on the fact that values of polynomial of degree k, if you take the differences, they form a polynomial of degree k minus 1. So the van der Korput tells you if I want to understand any sequence an, right? Let's not again look too much at the averaging. I need to understand what's called the bilinear sum an plus h. Okay, so that's you're trading, which seems counterintuitive, right? Because you have a single linear average and you are trading it with a bilinear average. So generally you don't improve your situation. And in dynamical terms, generally indeed you don't improve, you make your situation much worse, because, I've traded just one polynomial average into a product of two, right? So it is true that in general, van der Korput makes your life worse, and you can't really use it. But the point is that, the point is that generally it is much harder to study this expression, that bilinear expression, than the original one, but it is not always the case. And here I give you a reason why. Essentially, this is the proof why n squared alpha is equidistributed, right? So if you look at n squared and n plus h squared alpha, and you have characters, so e of something is e to the 2 pi I something, right? Then you see you've started with a product of polynomials of degree 2, and you end up with a linear phase. So the n squared is gone. And the point is, let me go back. In the van der Korput here, the h is fixed, right? So when you look at the right-hand side, you first sum over h, and in the inner sum, the h is fixed. So you only have a sum over n, right? So that's the thing, which means, for rotations, you instead of n squared that you started with, you somehow reduce the case to linear. So you have n times 2h alpha. And h squared is fixed, so you can forget about this. It just goes away. And if you go to higher polynomials, you can imagine you apply it many times, right? So if you want to know that n to the 4 alpha equidistributes on the circle, you would apply it. If you apply van der Korput once, you go down to n cubed, apply it twice, you go to n squared, apply it 3 times, you go to n, and then you have a geometric progression, which makes your life easier. One word of caution, even in this simple computation here, is that you reduce quadratic terms into linear terms, so you have n, but the frequency changes with h, right? So that's kind of the trade-off. You have 2h alpha, and you don't have, so if h is fixed, you have a fixed frequency, but it changes with h. So it means, what you need to show, if you look at this, is that for most h alpha behaves well, is irrational with, well, if you just want convergence, right? So if you just want small O of n, you just say that h alpha is irrational for any h integer and alpha irrational. If you want rates, so here I said, Green and Tao did nil translations with a saving, but in fact you can do rotations with a saving. That's much easier. And then you need to know, how close to rationals your number your number h alpha is. So that's kind of the thing. Yeah, and that's essentially the only method to show equidistribution along squares. It's very different than what we've seen for multiplicative function or primes. Here, there is no type 1, type 2 that would work. Basically van der Korput is the only thing. The reason being that, the heuristics behind multiplicative functions or, say, primes is that the good model for primes is a sequence of random variables. It is not the case for polynomials. So somehow polynomials are not random, right? They are on the opposite side, and you also use different methods. And for this reason, it is interesting. One question that, just to show you why this is kind of an interesting thing, I don't think at this point, we know an example of a dynamical system which would be equidistributed along squares, but not along cubes. And the reason being is that essentially in all the known examples, which are not that many, so these two, more or less, whenever you apply van der Korput once and it helps you, if you apply it twice, it helps you even more. So it means, you know, if I want to get cubes, then I just, you know, so basically what happens if I can get squares, this means I can apply van der Korput. So far, that's the state somehow. And if I can apply van der Korput once, I can apply it twice, and then I get cubes. So an example of a system like this would be interesting because it would mean there is a new method of showing equidistribution along primes, for example. Yeah. Maybe one thing that I want to mention, and then just maybe the last slide, is that part of the success with multiplicative functions, so the first topic, was because we had because we had the Matomaki-Radziwiłł theorem, so behavior of these functions on short intervals. For primes, we do have some results of that sort, but they are much weaker. And they are much weaker in the sense that if you ask for primes in a typical short interval, I think, and you know, typical short interval in the big interval from 0 to x, the size of the short interval should be x to 1/6, maybe minus epsilon. And for multiplicative functions, it was just any function going to infinity. So that's a big difference. And it's even more clear to see what happens with polynomials, right? So if you look at n squared, the gaps are very big, right? So you can, square root n is the kind of the boundary of the size of the interval that you could look at, right? Because, intervals shorter than root n don't have squares in it, or maybe there is one. So you can't hope for any results using short intervals. Yeah. And maybe last thing I want to say is that there is one new method that maybe Kosma will talk about in the second half. Yeah. So the subsets that we have discussed, so primes, polynomials, or multiplicative functions, we understand them in arithmetic progressions on short intervals. So what do I mean by that? Maybe squares are sparse, right? So let's focus on n squared. But if I look at n squared congruent to 2 mod 10, say, 2 mod 11, it's better, I think. It's good if. Then we have a very good understanding on how many squares we have and how they are distributed. The same with primes. Slightly worse with primes, but it's still promising in the sense that if I look at primes that are congruent to, I don't know, 1 mod 13 or 3 mod 13, we also know the distribution of pretty well the distribution of this. The thing is that it's hard to couple it with dynamics. So, okay, we understand how they behave, but in fact, can we use it to prove some dynamical theorems? And it turns out that there is one class of systems that probably Kosma will talk about, and these are called rigid systems. So a dynamical system is rigid if along a subsequence nk, if there exists a subsequence nk, such that T and K goes to identity. Okay, so if you take a finite rotation, right, of on Q points, then it's rigid along multiples of Q, and it's not only converging to identity, but it's equal to identity, right? And for example, as I said, understanding prime number theorem or squares for finite rotations reduces to the corresponding statements on arithmetic progressions in short intervals. To the first part that I just described. So the new idea somehow, or the new approach is that if you have a rigid system along the sequence nk, it in fact behaves like a periodic system. So it is not. So this is that I'm saying it behaves like a periodic system, and there are some similarities, but also one needs to be careful because first of all, the nk grows, so it's not that I have a fixed arithmetic progression; it changes in time. And second, it's not equal to identity; it's close to identity, right? So as I iterate it, it gets further and further away, right? So 2nk, 3nk, 10nk, and so on, right? If I iterate it more along the nk, I'm starting to move away from identity. So that's the other thing that one should take into account. But it turns out that if there is something to do. So if you assume something more maybe than rigidity with the results on from number theory, if you couple them, you can hope for some results on polynomials and maybe on primes. Yeah. So I think, yeah, that's it. I'll stop here.
Thank you very much for your seminar.
Thank you.
Are there any questions for Adam?
May I make just a small question? Sorry, Adam, can you say just something more about the difference between your recent results with Giovanni about the 2 primes and why it doesn't work for the 1 prime? Is that if I understood correctly?
You understood correctly. Yeah, let me go back. The reason is basically, if you look at the third line, so this is an expression involving D1 and D2. It's a bilinear ergodic, well, it's not, but say ergodic average, where the step D1, D2 is n to power C1. To get primes, we need C1 to be as large. So to say that this implies equidistribution along primes, we would need C1 to be of size 1/3, roughly, maybe minus epsilon, but 1/3. To get to semi-primes, C1 can be as small as we want. So basically, if there exists an epsilon such that it holds for D1, D2 of size n to power epsilon, then we get 2 primes. So that's the huge difference, right? It's how large the step is. Even for type 1, you can imagine. So like it's much easier to study arithmetic progressions of size n to the epsilon when I jump by n to the epsilon than if I jump by n to 1/3 or n to 1/2, say. So that's from the point of view of number theory, that's the reason why we can get 2 and we cannot get primes.
Okay, so the reason for this is hidden in the method, basically.
It's in the number theory input. Yeah, I don't think you can push it. It's not, I think it's really far primes and in terms of the input from number theory. Yeah.
Okay, so the Sarnak-Ubis, I think, method was completely different.
Well, so no, if instead of equidistribution you want density only, so really for horocycles, okay, so we talk about horocycles. If instead of equidistribution you want density, you can get rid of type 2 sums and study type 1 sums. And for horocycles, there is a huge difference between type 1 sums, so arithmetic progressions. These are somehow still the horocycle. It's still the horocycle. It's just, you can renormalize it. I mean, there are methods. Whereas if you want equidistribution, not just density, then you need type 2, which so what we use really is the recent breakthrough of Linden, Strauss, Mohammadi, and Wang, where they were able to get results of that sort for horocycles. Up to maybe 2 years ago, the only thing we knew is if you fix D1, D2, they are fixed once and for all, and then you let n go to infinity, then I can say something. And this is essentially Ratner. And this was used by Bourgain, Sarnak, and Ziegler to show Mobius for horocycles. Yeah.
Thanks.
Do we have other questions? So sorry, maybe I'll ask just one quick question because maybe I misunderstood. So you say that there are systems that do not satisfy the prime number theorem. That means that you don't have equidistribution along primes.
Mm-hmm.
And if you ask about density, is it still the same?
This we don't know, I think. This we don't know. So we create a subsequence of times, which most likely is very sparse, right? Which does, along which I mean, two different subsequences along which you converge to different limits, say. But density is an interesting question. Of course, in zero entropy, right? I mean, if you take Bernoulli shift everything, you can do everything. But yeah, yeah, we don't know.
Any more questions, comments? Okay, if not, let's thank Adam again.
Thank you for listening. Yeah, thanks.
Okay, so we can start.
Okay, great. So
okay, so let me introduce you. So it's my pleasure to introduce Kosma Kasprzak from Jagiellonian University, who will tell us about ergodicity along square orbits in rigid systems. Thank you.
Yes, thank you. Yes, thank you for the invitation to talk. So yes, I want to talk about the impact that rigidity has on ergodicity along square orbits, by which I mean the iterate of the transformation of the system at times n squared. So as Adam mentioned, if we want to have these orbits equidistribute for every single starting point, there's essentially no known other way to go than applying van der Kolk inequality in some sense. So having some algebraic properties that let us do that. So what I've been working on is trying to get this velocity in some other way. And in particular, it turns out that rigidity can imply this in a way that doesn't involve van der Kolk. So this is a really kind of optimistic new approach, in my opinion. So, okay, let's get straight into the main result that I want to talk to you about. I will explain everything. So, we are in the same setting essentially as in Adam's talk, where we want this equidistribution at every point. So, topological dynamical system. We assume unique ergodicity just because without it we cannot really go anywhere in terms of having these orbits equidistribute. And we impose some rigidity condition. So we say we have a sequence of integers under which these such that the qnth iterates of our transformation are very close to identity. So in particular, this is quite a strong condition because we not only want them to approach identity uniformly for all points in X, but we also impose a rate of convergence. And in fact, it depends on the next term of the sequence Qn. So it's a really quite strong condition. In fact, if this -4/5 were replaced by anything smaller than -1, there would already be no non-trivial examples. So it's almost too much to ask, but with this -4/5, there's still some interesting examples, which I will talk about later. Well, one interesting class of examples that I know of. So besides this rigidity, we impose this condition of coprimality on this sequence Qn. And this is also something that is essentially necessary to do just because we want to exclude, well, as Adam said, we expect these to behave somewhat like periodic systems, but for periodic systems specifically, we run into some troubles with well, distribution in congruence classes. So for example, squares don't distribute well modulo 3. So the 3-point system, even though it's very rigid and uniquely ergodic, will not be well distributed. Well, the square orbits will not distribute well, just because if you have 3 points and go around them, then the squares will only visit 2 of the 3 points. So we need something to prevent this sequence of times of rigidity from being, for example, divisible by a single number. So under this rigidity assumption, with this condition of coprimality, we will get unique ergodicity of the square orbits. Okay, so I would like to show you a sketch of the proof. So I might show something like this. So we will fix this starting point x, we will fix this continuous function f, and we look at the values of f on the orbit of x. So in particular, since we will only be focusing on this single orbit, we will introduce this function g of I that just lets us keep track of the values on this orbit. And the properties of the system x carry over to properties of the function g very nicely. So in particular, unique ergodicity tells us that tells us that initial segments of orbits of any given point, when we apply f to them, the average value we expect to be about the integral of f over the whole space. So in particular here, we know, well, we have control over average values of g over long intervals. So it should be converted to the integral of f if we take longer and longer intervals. And this rigidity condition on the system also carries over. So rigidity, if we apply it just to the orbit of the point x, tells us essentially that if we look at the orbit at times I and I plus qn, the resulting points will be very close to each other. In fact, they will be so close that we can iterate this argument, apply triangle inequality, and get that for not too large multiples of qn, if we take the orbit at 2 times which differ by this multiple of qn, they will still be close together. And after applying this function f, what that tells us about the function g is that it's somehow almost periodic. So these times qn and their multiples smaller than this qn plus 1 to the power 4 over 5, we can kind of subtract or add any such multiple to the input of g and not change the value too much. So okay, these are essentially the 2 properties of g that will suffice for us to determine that these averages over squares, to give us control over these averages. So how do we do this? Well, these averages are right now quite sparse. Yes, this sequence of squares has large gaps. The strategy will be to somehow use the fact that we can shift these inputs to kind of approximate the sum by a sum over something resembling a union of long intervals. And over these long intervals, we have ergodicity. So how do we do this? One natural approach is to, for some number capital N, consider the first n squares and just reduce them modulo one of each rigidity times qn. In order for this to happen, we of course need some constraint on n. Yes, in this reduction, we want to move things as large as n squared near 0 by these multiples of qn. Yes, so we need n squared to be less than qn times this maximal number of times we can subtract qn from n squared in order to still keep track of in order for the value of g to still be close to the original one. Now, and this is just for convenience, let us assume actually that let us assume that the sequence qn doesn't grow too slowly. So I want to assume this so that in this range over which I can do this for capital N, well, I can do this up to qn at least. This is pure, doesn't have a substantial impact on the proof, but I think it makes things much more intuitive. So okay, what we will do now is try to find some range close to Qn. So from some number slightly smaller than Qn to Qn for this capital N, such that in this range we have control over these quadratic sums. And then once we have control over the capital N in these ranges around the Qn's, we can then kind of bridge the gap into all the integers using these specific ranges as kind of building blocks. So for now, we just want to find some examples of these capital N which work, some range smaller than Qn. So okay, what do we do now? We have these reductions of I squared mod Qn. Capital N will be hopefully significantly smaller than Qn. So these are still kind of sparse in this interval. We still need something to, well, we want to kind of uniformize them so that they fill out the interval more evenly. And the way we'll do this is by what I think of as like taking each of these values of G at I squared mod Qn and kind of smearing it across a long arithmetic sequence. So what I mean by that is for any point y, if you consider the value G of y, we can use this rigidity constraint again, this time for the smaller rigidity time, so this Qn minus 1, and establish that, well, G at the point y is similar to the values of G along this long arithmetic progression ending in y, length Qn to the power 4/5 with difference Qn minus 1. So just subtracting small enough multiples of Qn minus 1. And if you know that G of y is close to each of these values of G along this arithmetic progression, then it also has to be close to the average value on that arithmetic progression. So this is very helpful to us because before we just had this capital N numbers in this interval Qn, but now we've replaced each of these numbers by an average over Qn to the power 4/5. So a very significant number compared to Qn. So now we have a lot more points covered, and now we can hope that somehow through this procedure we have actually hit every point smaller than Qn about the same number of times with these arithmetic progressions. So, well, let us find some way to quantify this. We have this sum of Gi squared Qn. This is roughly the average over the sums of G at I squared minus the small multiples of Qn minus 1. So how many times does a specific point J smaller than Qn appear in this average? Well, it appears every time. We can find a square of something smaller than capital N that when reduced modulo Qn will contain J in this arithmetic progression stemming down from it. So in other words, this is the same thing as saying for a given J, I want to look at all the squares of numbers smaller than capital N that when we reduce them modulo Qn end up in the arithmetic progression starting at J with difference Qn minus 1 and length Qn to the power 4/5. So here this bolded one is like the characteristic function of the expression inside. So it's supposed to be 1 if it's satisfied and 0 if it's not. So here we're doing like a sort of a double counting argument and realizing that for a given J, G of J appears in this double sum in the upper line as many times as many squares, as many small squares modulo Qn appear in this long arithmetic sequence. So this lets us kind of convert the problem now into a purely number theoretical problem. We wish to get like a uniform sum across the interval Qn. We now have a weighted sum of these values of G of J. And as long as these weights are similar for all the values of J that we consider, we will get essentially an ergodic average along an interval. So this is this analytical problem. Well, so this problem in number theory now we can use like purely number theoretical tools to tackle it. From analytical number theory, introduce some smoothing, transform the sum to a sum over all integers. by Poisson summation. There's some techniques that I don't want to get into since they are purely number theoretical, but if someone's interested, I'm very happy to talk about them later. And in any case, this number theory gives us that as long as capital N is at least Qn to the power 4/5, this double sum is roughly the same for each value of j, roughly equal to this fraction that is replaced by in the lower line. So as long as N is in this range greater than Qn to the power of 4/5, we can just estimate this by the average value of the function g over the first Qn integers, which we know is about the integral of f. And here it's scaled by this capital N, which is what we expect since we started with the sum of the first of g on the first n squares. So we expect to get n times the integral of f. So let me now say a few things about this. So first of all, this 4/5 in the problem, the statement of the theorem, it comes exactly from this number theory result, because we can make it hold only for capital N greater than Qn to the power 4/5. So that's the rigidity rate we have to impose. If we could somehow lower this lower bound on the capital N, under which we can control this double sum, then you would have a better result. And another thing is that so far we have not really used any properties of the sequence of squares specifically. So we have used the fact that it doesn't grow too quickly, so that we can reduce the squared modulo Qn. And now, essentially, the only other place where the specific kind of sequence we're using is important is in this number theory result. So squares are very convenient for in calculating sums like this. And as Adam said, we know a lot about their distributions, modulo integers, the different residue classes. So a result like how many squares fall into the specific logarithmic sequence, this is something we can tackle much more easily than for other sequences than squares or other polynomials. So all the dynamical steps I presented would work for essentially any slowly growing sparse sequence other than squares. Well, sparse just because these are the ones that interest us. Okay, but so far we have only covered capital N in this range from Qn to the power 4/5 to Qn. And now we would wish to extend this so that it covers all integers. So essentially what we need is to fill the gap between Qn and Qn plus 1 to the power 4/5. And then from that point on, we can use the same reasoning as before for these larger rigidity periods. So what do we do with these capital N in this range? Qn plus 1 could be much larger than Qn. So capital N squared, we can no longer just reduce it modulo Qn. This is way too much for this almost periodicity of G to handle. We don't have that strong of a rigidity constraint. And as I said, it would be impossible to have one that would allow us to do this in a non-trivial system. So we can no longer hope to just reduce everything to the interval 0 Qn. But fortunately for us, it turns out that if we only look at squares of two numbers that differ by Qn, and both are smaller than this value of capital N, then the difference between squares is actually roughly the amount that we can shift G by. So while we cannot reduce all the squares into one interval, what we can do is take these capital N values, which we square and consider the average of G over them, and split it into intervals, into these groups of consecutive ones of length Qn. So for the first group of length Qn, this is essentially what we just did with capital N equal Qn. And for the other groups, we want to do essentially the same thing, but not reducing it to the interval from 0 up to qn, but using this shifting by qn to reduce it to some other interval of length qn. So in particular, if we have this interval from kqn to k plus 1 times qn, then all these squares qn times k to qn times k plus qn, all of these squares we can reduce to this interval starting at qn squared times k squared. And this is actually within the limit of our rigidity rate of this almost periodicity. And then once we have done that, we have essentially the same situation as in the previous case, but it's on different intervals of length qn across positive integers. But since, well, we have unique equidistribution, we have unique ergodicity, so the fact that values of g at long intervals are roughly the integral of f, the average values of g over long intervals, this is like uniform across all intervals in the positive integers. So on each of these intervals, we can simply do the same procedure as we did in the previous step. And well, this would end the proof because now we have covered all the integers. So this is one way you could use rigidity to get these results about equidistribution. Let me mention one really interesting thing about this approach, which is that, like Adam said, if something works for squares, it will usually work for cubes and other polynomials, or at least other powers, in the same way. Here, there is actually a huge problem in extending this to cubes and further. Where's the problem? Well, for cubes, this number theoretical result still holds with some possibly slightly worse range, but still the number theory part is not the problem. And in fact, we could repeat the same reasoning and get a very similar theorem where we would replace a squared by a cubed in this thesis. But the thing is, to get that, the rigidity rate, we would have to replace from qn plus 1 to negative 4 over 5 to qn plus 1 to negative 3 over 2 or something like that. So it will be something significantly smaller than negative 1. So while the methods work, they give us a rigidity constraint which is not satisfied by any non-trivial systems. So quite interestingly, yes, I don't know if there exists a rigidity constraint which would guarantee us equidistribution over cubes or any other polynomials, only squares so far. So, okay, since we see that there are problems with examples for other sequences, let us maybe look at some examples which work with this rigidity constraint. So, well, the kind of classical example.
Can you again, sorry, can I ask?
Yeah, sure.
Can you repeat what is the issue with the cubes again? So is it you do the algebra and then sort of the rate that you get is simply you don't have examples? Is that the point, or?
Well, not that we don't have examples, but that. So, okay, the rigidity constraint here is this negative 4 over 5. This comes from the fact that we can go from qn to the power 4 over 5 up to qn. And then when we try to extend it above, we use the fact that these consecutive squares, or squares that differ only by this qn, which is very small compared to qn plus 1, you can imagine, but these squares differ by essentially a constant, essentially this qn times this upper bound for capital N. If we were considering cubes, we could do the first part the same, but in the second part, when you want to get qn consecutive cubes into the same interval, you would have to already subtract things of size qn times qn plus 1 to the power something greater than 1. So for us to be able to do that, the rigidity constraint we would need would have this constant negative 4 over 5 necessarily replaced by something which is just too much to ask. So to clarify, I didn't mean that we don't have any examples. I mean that it's provable that there don't exist any
I
non-trivial
see.
ones.
I see. Okay, thanks.
If this -4/5 is replaced by a constant smaller than -1. Sure. So about the examples for this constraint.
So sorry, just to
yes.
just to clarify again. So does this mean that similar result can't hold for cubes, or is it saying that the method of proof doesn't go through? So I understood that the latter is the case.
Yes, the latter is the case.
Okay.
Yes, with the specific method of proof. It could theoretically work. So the thing is, with cubes, if we assumed a rigidity rate of qn plus 1 to the power 4/5, like we have here, with cubes, we could handle capital N up to qn plus 1 to the power 2/5, not 4/5. So if we could somehow get this number part to allow us the range not from qn to the power 4/5, but from qn to the power 2/5 to hold, then we could actually join with this argument of separating into these intervals of length qn, we could produce a result which has a rigidity constraint for which we have examples. But this bound that we get from the number 3 part for cubes, it's only get worse. It is still a power bound. It is still something constant smaller than 1, but it will be greater than 4/5. And it is possible that the result holds this number theoretical part, so that this double sum can be approximated, so that this double sum is still relatively the same value for all of the j, even in this smaller range. I mean, even in the range for much smaller capital N, but I do not know how to prove that, and I strongly doubt that it would work. At least these analytical methods don't seem to work anymore.
Thanks.
Yeah, sure. Okay, so now for the example, unless there's any other questions, I'm happy to answer. Okay, so one classical example of rigid systems would be the toral rotations, in general group rotations, not specifically toral rotations. So rotations by an irrational angle on the torus. These are, of course, uniquely ergodic. And in terms of the rigidity, well, it's quite clear that they are rigid, since the rotation that sends one point close to itself will send all the points close to themselves. But we can actually get exactly the kind of rate of rigidity. And this has to do with the theory of continued fractions. So I hope you know some of it, and what I say now is just a reminder. For a given number alpha, we can consider its continued fraction expansion. And if we cut it off at some finite point, we get a rational number, which is a very close approximation of alpha. And if we now let Qn be the denominators of these rational approximations, they will satisfy this very strong rigidity. So since alpha is close to something natural over Qn, Qn times alpha is very close to an integer. So this norm here means the distance from the nearest integer. So for Qn alpha, it is very small. And in fact, we know that it's exactly about 1 over Qn plus 1, as in multiplied with Qn plus 1, it is bounded by 2 absolute constants. I think it just even 1/2 and 1 works. So we have a very good understanding of the rigidity, and well, what this corresponds to is the fact that the Qnth iterate of our transformation of the system takes every point very close to itself. And for the sequence of denominator specifically, we also very conveniently have this coprimality condition satisfied. Yes, another fact about these sequence of denominators is that for any alpha, they will grow at least exponentially quickly. But actually, they can grow much, much faster. So any kind of growth rate you could imagine, you will find an irrational number alpha for the sequence Qn grows at least that fast. So, okay, that's okay for these Tori rotations. This van der Corput method that Adam was talking about works. This is kind of the archetypical example where it works. So, well, so this is not the, so this is nothing new. So the actual example that I want to talk about will be in the space of skew product systems. So by skew product systems, I mean extensions of these Tori rotations. So systems where on the first coordinate, I am rotating by some irrational angle alpha, and on the second coordinate, I am adding a continuous function of the first coordinate. So this is a much broader class of system than Tori rotations. Just because we have this continuous function and we can pick any continuous function, there is much more variety in the behavior of these systems than just in the Tori rotations. And yes. So the example that I want to show you is if we have an irrational number and that Qn be the sequence of denominators that we just talked about. If we fix some weights an that satisfies some kind of asymptotic conditions and pick a function g given by its Fourier expansion with these weights ak, and here we have 2 pi times qa times k. So we take the waves at these times which are the denominators. Then for this particular function, the skew product system, it satisfies the assumptions of our theorem. So it will be uniquely ergodic and it will be rigid with the appropriate rigidity. And well, we can even extend this a little bit. For example, this an greater or equal than 1 over Qn plus 1, we could have this hold only along a subsequence and not everywhere. And in this GX, you could add some other terms with some other periods rather than QK, as long as we control the weights behind them. But this is kind of the simplest series of examples I can show you. And what I should say is that not for not every alpha, such sequence an can even exist. So for this sequence an to exist, we need Qn plus 1 to be at least Qn to the power of 5, and even grow faster than that, so that we can find an satisfying these asymptotic bounds. But as I mentioned, the sequence Qn can grow arbitrarily fast with the correct choice of alpha. So we don't have an example for every alpha, but for a large number of values of alpha, we have a lot of leeway in picking the coefficients and a large class of examples. And for these, for example, there is no real way to approach them via van der Corput theorem. So this is something that seems like a genuinely new approach to this ergodicity along squares, equidistribution along squares. Right, I had some intuition behind why this example works, but I see that I'm already a few minutes over time, so maybe I will just end here. So thank you for your attention.
Thank you.
Thank you very much, Kosma. Other questions? So can you give a quick intuition of how it works for us?
Yeah, sure. Well, so the way to approach this, well, so the good thing about these skew products is, well, first of all, I can maybe say that on the first coordinate, we just have this rotation by alpha. So this, we already know that the sequence Qn is very rigid there. And when we look at iterates on the second coordinate, we have a very convenient formula for them. So the mth iterates on the first coordinate, it's just rotation by m alpha. And the other, we are adding this sum of the values of g along an arithmetic progression of length m with difference alpha. And what we want to have this rigidity is we want this value for Qn to be somehow very small. Now this is somewhat unexpected because this sum Sqn of g of x, the expected bound for this is Qn, so it's much larger than 1, and here we want it to be small even in terms of Qn plus 1, in terms of the inverse of Qn plus 1. But this turns out to be satisfied, and well, the way to show this would just be to split g into these cosine waves, and on each cosine wave we know how the arithmetic, how to evaluate these sums of cosines of arithmetic sequences. So you could just evaluate them and check. But the reason why this is true is that we are taking here essentially the sum of g along these points x plus I alpha for I smaller than Qn. And these points, since Qn is this denominator, these points are very well distributed on the torus. So taking the sum over them, if you're taking the average over these points, it's almost like we're just taking the integral of this function g, which is just 0 by the definition. So there's a lot of detail to work out, but essentially that's why these periods Qn specifically related to alpha are so important to us, because these are the kind of optimal times to sample this beginning orbit of x plus alpha. And because of this, we have this, well, so for this to be satisfied, we need these an to be the law of 1 over Qn times Qn plus 1 to 4 over 5. So that's where the upper bound on an comes from. But, well, with an just satisfying that, we could even have them be 0 and have g be 0. So this definitely doesn't imply unique ergodicity yet. And indeed, unique ergodicity is given by this lower bound. So for unique ergodicity on skew products, there's actually a very convenient way to check whether a system is uniquely ergodic. It's enough to check that no multiple of the function g is a co-boundary. So, and this is something this is an elementary result essentially. The fact that on skew products, unique ergodicity is equivalent to ergodicity is a result by Furstenberg in even a more general case. And to show that ergodicity is equivalent to this statement, it's enough to assume that the system is not ergodic, take an invariant function, which is not constant, use the Fourier decomposition of the function, and then somehow this Fourier decomposition gives us a solution of this equation. And the thing is, if such an equation was satisfied, then our system would be much more rigid than it can be with our choice of AK. So for example, if such an equation was satisfied for k equals 1, then just if we take the STQN of this, on the right-hand side, we get just a telescoping sum. So it all reduces to the value of psi at 2 points, which are very close since, well, if we're doing this by this time TQN, then TQN times alpha for appropriate values of t will be very close to an integer. So Qn times alpha is at most 1 over Qn plus 1 away from an integer, as long as t is not too much greater than Qn plus 1. We know that this is just a measurable function. It's 2 points that are very close to each other. And then in measure, it would be essentially 0. Modulo 1 because we're working on the torus, but g is somehow defined on the real line. So we have to include this modulo 1. And what this would mean is that, well, so far we know that SQN of g of x has this kind of bound on it. From this, by triangular inequality, again, we can conclude that this STQN of g for t smaller than Qn plus 1 to the power 4 over 5 is somehow small. It's still approaching 0. But if our system was not uniquely ergodic, then our system would be rigid even for times t up to Qn plus 1. And well, we have enough control over these arithmetic progressions, over these sums of cosines and arithmetic progressions, to know that if we go this with such large multiples of Qn, we cannot have rigidity anymore. So at this point, this sum will no longer be very small. It will somehow oscillate, and it will not be close to 0 mod 1. Yes, so that would be the.
Okay. Thank you. Other questions? Sorry, it's a bit outside of what you talk about, but what do we know for IETs instead of rotations?
I have not thought about this.
Yeah, it's a bit, sorry, it's a bit outside what you talked about. I was just curious.
Yes, so I don't know. It's possible that you can do similar things. I have not thought about it.
Okay, if there are no further questions, let's thank Kosma again.